Good morning, everyone. So today we continue to talk about the finite element method, and we'll talk about chapter 5, the FE analysis of triangular elements. So triangular element is one type of two-dimensional element, and after this chapter we'll talk about the other type of 2D element, that is the rectangular element. So today we will show you what's the FE procedure and how do we solve the triangular element using the FE method. So part 1 is the FE analysis procedure of triangular element. So the approach we show here is different from the approach you learned from the mechanics of materials and from other lectures, because here we're using the finite element method, not the energy method or some other methods. So first let's have a look 3-node triangular element. So whenever you say 3-node triangular element, which means this triangular element, it has 3 nodes. And in other case, you will also say, for example, 6-node triangular element, which means this one element it contains 6 nodes or even more nodes. So be noted of this. So first we look at the simplest case, which is the 3-node triangular element. So we have a triangular element here, and so we have 3 nodes, node 1, node 2, and node 3. We said it's a 2-dimensional case. So for each node, it has two degree of freedom. So for example, for node 1, it has the degree of freedom in x direction and the displacement in y direction. So similarly, at node 2, it has the displacement in x direction and the displacement in y direction. Node 3 is the displacement in x direction and the displacement in y direction. So in total, for this 3-node triangular element, so whenever you mention this the element, you also try to be accurate or try to be exactly. So you should say 3-node triangular element. So for this 3-node triangular element, we have the displacement vector. So displacement vector, it has 1, 2, 3. It has 6 components. So which is the degree of freedom of each node. And for the node forces, it also has 6 corresponding node force components. Okay, so each, for example, px1 is corresponding to u1, py1 is corresponding to v1. Okay, so this is the displacement vector and the force vector. Let's say we have mentioned before for the finite element calculation. So in a FE calculation, we want to solve the displacement. Okay, if the displacement field is solved, and then we can use the geometric relationship or geometric equation, or sometimes we call it the string displacement relationship, to solve the string in the system, or we should say in the FE course we should say deformable body. And then we can use the constitutive relationship to solve the stress field. So the key step is to solve the displacement field. So we have said for the FE analysis, we give a trial answer. So for example, here we guess the answer, and then we solve the coefficients. We set up the stiffness equation and we solve the coefficients, and then everything is solved. So first we give the trial trial function for the answer. So we need to solve the displacement in x direction and the displacement in y direction, and both of these, they are a function of the coordinate, which means when we move the point inside the triangular, the displacement is moving, and this is the displacement in x direction, and then this is the displacement in y direction. They are a function of the coordinates. Okay, so because this is a two-dimensional case, so we have two variables. If you remember, in the previous lecture, when we talk about the bar element, if it's only one-dimensional, we only have one variables. But this is two-dimensional, so we have two variables. So we say, then we need to introduce more coefficients. So here we use the simplest case. So we use the first order. So we use the first order term. So we ignore like x squared, y squared, the higher order terms. So, and then we introduce the boundary condition. So we introduce the boundary condition because we assume the displacement at the node is known. So then that's why we want to introduce the boundary condition. And we introduce the boundary condition and we solve the equations. Then we can have, so this is mathematics. So we put the boundary condition back into those formulas, and then we use the node displacement like u1, u2, u3, and other like v1, v2, v3. Like we use the node displacement to express the coefficients in the displacement field function. So this is mathematics. So you should try yourself or practice yourself whether you can get those or not. So then we solve this equation. We use the node displacement vector to express or to represent those coefficients, and then this is mathematics. So in this formulas, the big A, the variable big A equals to those, and the small letters like those coefficients A1, B1, and C1, they equal to those. Okay, they equal to those. Well, here the big A, the capital A, is the area of the triangular, and for other parameters like A1, A2, A3, they can be obtained like by replace 1 with 2, replace 2 with 3, replace 3 with 1. So kind of there's a rule here. So it's what does this mean? Let me draw it here. So which means here this sentence means A2, B2, C2, A3, B3, C3 are obtained by replace those letters or those numbers. So which means we have the expression or equation for A1. So from here we can get A2 equals to what? A2. So we replace so 1 with 2, and then in the right hand of the equation also we replace. So this tells us we replace 2 with 3, and replace 3 with 1, and minus we replace 3 with 1, replace 2 with 3. So in this method we obtained A2. So similarly A3 will be equals to, so we replace 1 with 3, right? And then here we'll replace here the 2 with 3, and the y we replace 3 with 1, and minus we replace 3 with 1, x1, and y we replace 2 with 3. Okay, so in this way we obtained A3. So this tells us, although we have a lot of equations, but there's a rule here. So you don't need to remember all the equations. You just need to remember these 3, and then you can get other 6 equations. Okay. So this is in this slide. There's nothing new. It's just the mathematics. Okay, just mathematics. You just need to practice and to see if they are correct or not. And even for those equations, you don't need to remember in your mind. Just you need to know and how they are calculated. And if you do your calculation, how you can get those formulas, get those coefficients, and how to use those coefficients. So we never ask the students to remember those formulas, because you cannot remember forever. The key point is you need to know the procedures, you need to know the ideas. Okay, so by replace those coefficients, then we can rearrange. Okay, we rearrange the node displacement function. So for the x direction, and this is for the y direction. So in the x direction, we can rearrange in terms of the shape function. So we have, so here our unknown variable is the u1, u2, and u3. It's the node displacement, and then behind the coefficient of u1 is the shape function n1. Coefficient of n2 is the shape function n2. Coefficient of u3 is shape function n3. So similarly here is n1, n2, n3. Okay. So then we arrange in the. I'm sure you have still remember this form. So we will always arrange the node displacement function in terms of the node displacement vector times the shape function matrix. Okay, so this is the shape function matrix, and this is the node displacement vector. So we unify all the different elements. We unify all the displacement function for all different types of elements in the same term or in the same format. So people, or even for the program, be easier for the program to handle. Okay, the only difference is for different elements, the shape function matrix is different, and the node vector will be different. Okay, but it's always is the shape function times the node displacement vector. So for this 3-node triangular element, this is the format for the shape function. Okay, for the shape function. So we have 3 shape function, n1, n2, n3. Okay, and here also you need to be careful here. So this is the x direction and this is y direction. For both directions, they share the shape function. So for example here u1, u2, they use n1, and for second u2 and u3 they both use the n2, and the u3 v3 they both use n3. This is because of the mathematical view here. So from this mathematical calculation, we found this rules. We found these results. Okay, so there's nothing more, or there's no additional reasons. It's just because of the mathematics. Okay, then because of those, they share the shape function. So we arrange the shape function matrix as this. And if you do the calculation, for example here, n1, the first row times this the node displacement vector, you get n1, u1, n2, u2, n3, u3, and in the second row n1, v1, n2, v2, n3, v3. Okay. And then here we already mentioned n is the shape function matrix, and this is a very important concept, and we will talk more and more about the shape function matrix. Okay, and in this case, in this 3-node triangular element, the shape function equals to 2a 1 over 2a and then ai bi x plus ci y. Okay, here you see also I can be 1 2 3, or it can be a loop. And this is also, this equation also is from the mathematical before here. So it is a mathematical. It's all from the mathematics. So this equation, it tells, it represents 3 equations. So from here we know, from here we know n1 is represent 3, okay, because here I can be 1, can be 2, or can be 3. So n2 or n3. Okay, so from here we know n1 equals to 1 over 2a, and then it's I equals 1a1 plus b1 x plus c1y. Okay, and from this we also know n3 equals 1 2a, and then a1 I equals 3, a3 plus b3x plus c3y. Okay, and for the coefficients a1 b1 c1 or a3 b3 c3, you can check the previous the previous slide will tell you the expression for those coefficients. Okay. Okay, let's have a look at the physical meaning. The physical meaning of those. So when u1 equals to 1, u2, u3 equals to 0, and then ux, okay, ux equals to n1. Okay, what does this mean? So u1 equals to 1, so this equals to 1. Let's have a look at the equation here. And u2 equals to 0, so which means we can eliminate this term. And u3 equals to 0, so we can eliminate this term as well. And then which means if u1 equals to 1, other two display equals to 0, then we get u equals to n1. Okay, so and then we translate this into the language. So which means n1 means the elemental displacement when u1 equals to 1. Okay, when u1 equals to 1. So this is the physical meaning. This is the physical meaning. If you learn some course, they tells you the physical meaning of some equation or some variables. So this is mathematics. So this is mathematics. So mathematics, which means you get those from those mathematical operation. But always we want to translate those mathematics into physics, because once you translate into physics, you can understand it by your sense, or you can remember it longer. Okay, so which means this tells us the physical meaning of the shift function. So n1, the physical meaning is the element displacement. Okay, it's the element displacement under the condition u1 equals to 1 and other equals to 0. Similarly, we can get like the physical meaning of n2. So n2 is the element displacement when u2 equals to 1 and u1 and u3 equals to 0. All right. Okay, this is the physical meaning, and you should understand this. Also, you should be able to extend to other scenarios. Okay, so we'll talk about the shift function more in the following slide, in the coming slides. Now we have solved the displacement, know the displacement formulation. Okay, what I say solve is we have managed to arrange it in terms of the shift function matrix times the node displacement vector. And then let's have a look at the string formulation. So the procedure for this is similar to the bar or even for the beam element. So if you understand those, and then for this part it'll be easier to understand. So for the string formulation or for the string displacement formulation, we use the geometric equation for the two-dimensional case. Okay, this is for the two-dimensional case. We already know this, so we don't repeat here. So this is here we just write this formulation in another term. So this is, and in this term here, this is the operator matrix of the string displacement equation. Okay, this is an operator, and this is the displacement, the node displacement vector, and this operator equals to the coefficient here, or equals to the term before the displacement vector. Okay, this is the operator. What's the exact meaning of the operator? So we introduce this operator because we want to simplify the writing, or simplify the equations. So then let's have a look. Continue. So then we put in the displacement formulation, which means we have the displacement formulation in terms of the shape function and the node displacement vector. Then we introduce those equation or formulation into the geometric equation here. Okay, geometric equation. So we have the displacement. Okay, we replace this displacement with the shape function times node displacement, and then we manage to write this string, the string in the triangular element in terms of the B times Q. Okay, this is important because we want to, again, this is similar to the bar and beam element. We want to arrange the string formulation in terms of the string displacement matrix and the node displacement. That is the string displacement matrix and the node displacement matrix. We want to arrange in this format. Then we can use it to obtain the stiffness matrix equation. Okay. So here B is the string displacement matrix. Okay, and this is the mathematic, and again, so because we arrange this, so which means the B will equals to those parts. So this part is B. Okay, this is B, and then we can for the B, and then we this is we just say this is the operator. Okay, so which means the matrix B is the partial derivative of those shape function. Okay, of those shape function, and we know the exactly formulation for the shape function. So we put in the shape function formulation. Then we have the value for the B matrix, and we can see. So this is important. So if you say the B matrix, you will know there's no variable here. There's no variable here. So it's all coefficients, or it's all constant. There's no variable here. So which means here, if you look at this equation here, so the B matrix is a constant, and then this is the node displacement matrix. Okay, and once it's solved, and it's a constant. So which means the string formulation, the string is a constant. It's not a function of x, y. It's not a function of the coordinate anymore. So which tells us the physical meaning. Okay, this tells us the string formulation, or the string distribution in the three-node triangular element is a constant. So it's a constant string element. So this is a very, very important concept, or this very, very important conclusion. This helps you to understand your problems, or help you understand your results. So this tells us whenever you use the 3-node triangular element, the string in the element is always a constant. So don't be confused or don't be misunderstanding this. Okay, because of this is a constant, so we said we don't recommend to use the 3-node triangular element, or sometimes we call it the linear element, because it's constant and you need many more elements to approximate the nonlinear problems. Okay, which means you need to use very small mesh or to increase your element number. Otherwise, you don't get accurate answer. Okay, so this slide is very important. This is the theory, okay, behind some conclusion, behind some sentence in the manual. Okay, so if you understand this, you will understand why this element is not recommended in the FE calculation or in the FE analysis. And then the stress formulation. Okay, so this is the string formulation, and this is the stress formulation. This is based on the constitutive relationship. So we said whenever we talk about the constitutive relationship, it depends on the material you use, what types of material, what kind of material. Okay, so it's which means depends on the Young's modulus, the Poisson ratio, and we said we have made 5 assumptions at the beginning of the lecture. So we use the linear elastic, and we use isotropic, and we use continuum material. So based on those conceptions, we can write the stress formulation in these terms, or in this expression. So when your material is not linear, or if your material is hyperelastic or is anisotropic, or if a material violates the assumptions, you shouldn't use this. So this, you should have this concept very clear in your mind whenever. So when under which condition you can use these formulations, and under which condition you cannot use those formulations. Okay. So, and then this is for the simplest case, which is the linear elastic and isotropic material. We use this to solve the stress formulation, and we said this D is the stiffness matrix, and we can write as D times the string. Okay, D and times the string, and then for the plane stress problem, because we are talking about the 2-dimensional problems, and for the 2-dimensional problem we have 2 cases. First is the plane stress, and second is the plane strain. And for different problems they have different stiffness matrix. And then so if you don't understand those, you should check the book, the elasticities. Okay, so we don't give too much details here. So this is not the inner scope of our lecture. Okay, and then we arrange the stress formulation in terms of the stress displacement matrix times the node displacement vector. So we write in these terms, because in the end we want to assembly, or we want to put into this equation, that is the stiffness equation. Okay, and then this is the P. Okay, PE. Okay, because we want to put all those into this. That's why we write all the variables in those terms. Okay, in order to easily put or easily translate into this stiffness equation. Okay, that's the aim. And then after we have the formulations for the strain and the stress, then we can have our potential energy. Okay, potential energy. Why we get the potential energy? Because we said we use the minimal potential method, and so to obtain the stiffness equation. Okay, so kind of this potential energy is the function. Okay, is the function. And the potential energy is inside the element is the potential energy inside the element is the stress times the strain. Like this is the internal energy, and this is the external energy. So which means this is the energy done by the external force, by the external force. So there's a body force here. The body force is the energy because of the weight of the element. And sometimes you have your weight is very small, so you can ignore this. And then this is the pressure, okay, or the force at the node, okay. And then because in the previous slide we have managed to arrange all those in terms of the matrix times the node displacement vector. So then we can arrange like this, and then this is our body force and the loads. We also will arrange in terms of the node displacement vector, okay, always in terms of the node displacement vector. So in the end, we have this formulation. We have this formulation, and here K is the important concept. Is the element stiffness matrix, okay, element stiffness matrix, and the expression or the formulation for the element stiffness matrix is similar to the one we obtained for the bar and for the beam element. So it's the B matrix times the D is the material stiffness matrix, and then it's the B and B matrix, okay. And then the B is a constant coefficient matrix, and therefore we have the exact format for the K, okay, exact format for the K. So we can see for the K matrix is very complex. So it's impossible to remember it in your mind forever. But don't worry. So you don't need to remember those formulations. It's too complex. What you need to know is how to use them, or whenever you want to do your own calculation, or whenever you want to do your own coding, then you need to use those equations to help you to do the coding, or to help you to solve the element stiffness matrix. And then the other thing you need to remember is the procedure, how you obtain those stiffness matrix, how you obtain the D matrix, B matrix example, and once you know the procedure, then you can follow the same procedure to solve other elements. Okay, this is the knowledge you need to learn. You need to know. Okay, and in the formula, P is the element equivalent node forces and they equal to those. We have mentioned the equivalent node forces. So we said all the forces they need to translate to the node forces. Otherwise, you cannot introduce them into the stiffness equation. Okay. So we will also talk about this, how to do this for the triangular elements. We already mentioned it for the beam elements. And then the element stiffness equation can be obtained by do the partial derivative of the potential energy to the node displacement vector. Okay, and then we obtain the element. Remember, this is the element stiffness equation. Okay, so this is the whole procedure to obtain the stiffness matrix equation, stiffness equation for the element, for the triangular elements. So once you have those, then you can assembly to get the stiffness matrix for the structure, for the entire structure. Okay, and then everything be solved, and everything else will be similar to the beam and the bar element. Okay, so now let's have a look at the part 2, the shape function of triangular element. So the shape function of triangular element. We said the shape function is very important, and it tells you a lot of information about the elements, and can help you understand the element. Okay, so first, there are several properties, or actually it has 4 properties. First, let's have a look at the first property. The first property. So for the shape function, we said for the triangular element, it has